All right, so we're going to start from scratch doing a problem that involves linear programming. Um, so my father-in-law used to own a carpet store, and so some of this is not completely accurate, but we are going to go through because it makes for a nice, easy problem to work with. But my father-in-law, just to kind of understand the problem, we're going to go through these different aspects of the problem and go through a linear programming example from the very beginning. So there has to be at least 6 crews working. One of the stipulations that he wants to put in place is that he wants to keep 6 crews working all the time from his carpet store. Sometimes they go out and they lay carpet. Sometimes they're tearing up carpet. But there are 6 crews working. Sometimes it's a residential building or home, or sometimes it's a commercial building. So, and then within those 6 crews, he wants to have 12 certified installers. He also wants to have 12 apprentices. An apprentice, a certified installer, is somebody that is self-insured. So if they mess something up in a house or a building, their insurance will cover their mistake. They bring the carpet through the window, they'll pay for the window. An apprentice is just somebody who is learning the trade from one of the certified installers. And he wants to have at least 12 apprentices because a lot of times the certified installers find a job somewhere else and need to be replaced with your next best apprentice. So he pays the installers $30 per hour. He pays the apprentices $16 per hour. There are 2 different types of crews that he sends out. One, we're going to call it an X crew, as 3 installers and 1 apprentice. So that's a very high technical crew. That might be a crew that's laying carpet on a set of stairs. They need a lot of people who know what they're doing, but it takes time. And maybe the apprentice is just going and getting tools for the people who are laying the carpet. And then a Y crew is 1 installer and 4 apprentices. And so this would be a type of crew that's maybe just going out to a building to rip up a bunch of old carpet, and they just need a lot of muscle work, but not a whole lot of brains. So there's not only 1 installer, but 4 apprentices. And so the question that we want to find here, and this is our objective, is how many of each type of crew, so how many X crews and how many Y crews, should there be to minimize the expenses. So step 1 in this process that we're going to do, called linear programming, is to minimize our expenses. And so we're going to come up with a equation for our cost, and we want to minimize that cost. But our costs involve the X crews and the Y crews. And so we have to figure out how much does it cost my father-in-law to have an X crew out in the field working somewhere. Remember, there are 3 installers, and an installer gets paid $30 per hour. And there's 1 apprentice, and that apprentice is getting paid $16 per hour. So 3 times the 30 is $90, plus the apprentice is another $16. That's $106 for each X crew. So every hour that they're out there in the field working, it cost my father-in-law $106. Plus, every Y crew is also getting paid. They have 1 installer, which is $30. They have 4 apprentices. 4 times 16, well, that's $64. Plus the $30 is $94 per hour for each Y crew that's out in the field. This is our objective. Now, this is something we're going to come back to throughout this process, but the first thing that you want to do when you start one of these problems is to figure out, what is your objective? What's the whole reason for doing this type of problem? So there's our objective. The second phase in this process is to come up with the constraints. So if I didn't have any constraints and I really wanted to minimize costs, I wouldn't send anybody out there. We're just going to close up shop, and then I won't have any costs. But there are some constraints. We don't want to do that because he wants to have at least 6 crews working. He wants to have at least 12 certified installers and at least 12 apprentices. Well, that creates a little bit of a problem because we have to have some minimum standards, or at least some people out there working. We're going to have some costs. So we're going to have some constraints. And one of the constraints is that if I take my total number of X crews and my total number of Y crews, I want to have at least 6 of those crews. So it might be 4 and 2, or 2 and 4, or 3 and 3, or 0 and 6, but that has to be greater than or equal to 6 total crews. Could be 6. It could be more than 6 crews. But again, I want to minimize my costs, so more than likely it'll end up being only 6 of those different types of crews. But then he also only wants to have 12 certified installers. And so again, we have 3 different types of crews out in the field. An X crew. Well, how many certified installers are on each X crew? There are 3 certified installers for each X crew, plus for each Y crew there's 1 certified installer, so that's plus 1 Y. So I have 3 certified installers for each X crew plus 1 certified installer for each Y crew. I need to have at least 12 certified installers. So it could be more, but that has to be greater than or equal to 12 certified installers. So this equation is an equation that describes my certified installers. That's a constraint that I have. I have to have at least 12 of them. I also have to have at least 12 apprentices. So in each X crew, I have 1 apprentice. So that's 1X, plus I have 4 apprentices for each Y crew. So for each Y crew that's out there working, I have 4 apprentices working in that crew. So it's 1 for each X crew plus 4 for each Y crew, and I need to have at least 12. So there's another constraint. Another constraint would be that my X crews, I can't have negative X crews, that's going to be greater than or equal to 0. And I can't have negative Y crews, that's going to be greater than or equal to 0. This list of 5 different inequalities are my constraints then. So I want to come up with what is my minimum cost going to be, considering that those are my constraints. That's the second step in this process. So the third step in this process, so I'm going to label that over here, the third step in this process is to graph what is called a feasible region. And what that entails is graphing these 5 different constraints. And so I'm going to go ahead and make a graph here so that you can see this, and you should be doing this along with me on your paper. And so what I'm going to do is graph these different equations. First of all, I'm going to focus on these 2 down here. If I graph both of those, essentially that means I'm in the first quadrant. So my X values are greater than or equal to 0, so I'm at 0 or 1, 2, 3, all the way up to, I'm going to go up to at least 12. I think I'm going to need up to 12 on in both of these directions. So I'm going to be somewhere in the first quadrant. I could put a line here and shade in this area. I'm just going to know I'm to the right of the y-axis. Also, my y values have to be greater than or equal to 0. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so my y values are above the x-axis. My x values are to the right of the y-axis, and so I'm in the first quadrant. And so now I want to graph these 3 constraints. And the first one is that x plus y is 6. So if I were to make a table of values here and plug in 0 for x, well then y would be 6. If I plug in 0 for y, then x would be 6. And so that's going to be a point at 0, 6 and at 6, 0. And if I were to connect these points, this is my constraint, and it has to be greater than or equal to 6. So I'm in this area out here so far. So let's graph the second equation here. And again, I'm going to do this by making an x and y table and plug in zeros. You could solve it for y and do it that way. But if I let x be 0, then y has to be 12. And if I let y be 0, then x has to be 4. And so we have a point at 0, 12, which is up here. And we have a point at 4, 0, which is right here. And if I think my slope might be, nope, it's not. Maybe it's -3 down here, yeah it is. So I have all these points here. Here's the line that represents that inequality. And since it is, if I test the point 0, 0, both of these are going to be 0. 0 is not greater than 12. This point's not going to work, so I'm still out in this area. And then if I graph my third constraint, I'm going to again make a table of values and plug in zeros. So if I let x be 0, then 4 times 3 is 12. And if I let y be 0, then x has to be 12. So there's a point at 12, 0, and a point at 0, 3. And if I were to graph these points, then I'm going to have a line right here. If I test the point 0, 0, and I put 0 in for x and 0 in for y, it's going to be 0, which is not greater than 12, so the point 0, 0 is not going to work, and I would be above this line here. So my feasible region is the area that's bounded by these three lines, and I'm also in the first quadrant, which means my feasible region is this area right in here. So that might look ugly, but that's my feasible region. The next thing that I want to do is the fourth part of this, and that's find my vertices in this feasible region. I could test a point right here, but if that point works, so does this point, and I'm having one less x crew and one less y crew, and that point would be less than this point as far as if I'm considering my cost. And so my minimum cost is going to show up at one of these vertex points, either this one, this one, this one, or this one. And so I've got to identify what those vertices are. So the first one, I'm going to use that one as 0, 12. Okay, I could label that, maybe I'll label that point A here. And then I have a point B at, this is the point 3, 3. So point B is at the point 3, 3. Point C, which is right here, is going to be at the point 4, 2. And then point D is at the point 12, 0. And one of these values, when I plug them in for x and y in my objective function, is going to give me my minimum cost. And so my fifth step now is to plug each of these into that equation and figure out how much it's going to cost me. If I plug in point A, which is 0 for x and 12 for y, I would take 94 times 12, which is $1,128. So that means every hour, if I go with 12 x crews and 0 y crews, it's going to cost my father-in-law $1,128. If I plug in point B, which is 3 for x and 3 for y, I would take 106 times 3 plus 94 times 3. Well, that's going to be $600 an hour. If I plug in C, which is 4 for x and 2 for y, 106 times 4 plus 94 times 2 is $612. And if I plug in point D, which is 12 times 106 plus 94 times 0, that's $1,272. So you can see there's a wide range of different options that I have here, but to minimize my cost, to minimize the cost for my father-in-law who owned this carpet store, he would want to use point B, which is to have 3 X crews and 3 Y crews. And you might think, well, that's maybe not that exciting, but it is exciting if you think about it this way. Let's say he was in business for several years, but let's say that he was in business for 39 years. And so let's say for those 39 years, he went with the next best option, which is 4 and 2. That means he's losing $12. He's losing $12 every hour. So if it's $12 every hour, then I would want to know how much is he going to be saving in a day. And so let's assume that they're working 8 hours a day. We would take 12 times 8. That's $96 a day that he would be saving if he knew linear programming. Well, in a week, that's 5 days in a week. So if I multiply that times, let's say 5, that's $480 in a week. Well, let's say he gave his people that he worked for him off 2 weeks of the year. So that would be 50 weeks in a year. So if I multiply that times 50, well, that's $24,000 that he would save in a year. And over the period of his business, which was, let's say, in business for 39 years, we would multiply that times 39, and that is $936,000 he would have saved just by knowing what you guys now know, which is about linear programming. And that's kind of a big deal now. And so if you could convince somebody in a business that you could save almost $1 million by knowing what you guys now know about linear programming, that might be something that they would want to listen to. So this is the first example, and I'm going to stop the video and we'll go to the next video to go through the second example here.